Alright guys, we're going to take a look at balancing half reactions. So the front page of this is the notes, and there's two more examples on the back that we'll take a look at. So oxidation reduction reactions, or redox reactions, involve the exchanging of electrons between two elements, which causes them to change their oxidation numbers or apparent charges. The balancing of these reactions is not just about balancing the number of atoms of each element, but also the number of electrons lost or gained by the atoms. A key way of looking at these reactions is to separate the reactions into the oxidation half reaction and reduction half reaction. These are both chemical reactions, but each focuses on one part of the overall reaction. It allows you to see the charges, balance them with electrons, and then see how the two reactions would need to balance with one another to put them back together. So we're going to take a look at this example. This is a redox reaction. So we want to determine, or we can determine that it is a redox reaction by assigning oxidation numbers to each of the chemicals. So this is always a method. If we are asked if a reaction is redox, we can always check by assigning our oxidation numbers. So our first chemical, bromine, it's by itself one element. There's no charge written, so it would have an oxidation number of 0. We've got iron by itself, but it has a charge, so its oxidation number would be that charge, positive 2. Bromine by itself has a charge, so its oxidation number should match it, negative 1. And same with iron, so positive 3. Excuse me. By assigning the oxidation numbers, we not only see that they are changing, they're not the same on both sides for each element, but how they are changing. So this allows us to see what is oxidized and what is reduced. We can then separate the reaction into the reduction half reaction and oxidation half reaction. So I always like to find my reduction reaction first. So we are going to look for a chemical where its charge, going from the left side reactants to the products on the right, its charge goes down. It is literally reduced. So bromine goes from 0 down to negative 1. That is a reduction. We can see iron goes from 2 to positive 3. That's going up. So bromine is going to be our reduction half reaction. So we are going to take the pieces for that and just create a reaction. Br2. For now, we can leave off the states of matter. We'll add them back in at the end. They don't change during the reaction. And then it forms Br minus. So those are the only two pieces changing that cause this reduction. We can do the same thing for our oxidation. In oxidation, we want the charge to go up. So we've got iron 2 plus going to iron 3 plus. Our charge is going up. So we've got Fe2 plus forming Fe3 plus. So now that we have that, we can start balancing these half reactions. And we're going to follow the steps below on your paper. So we're going to start with these 3 steps, and we're going to do it for each of the half reactions. First, we're going to balance the atoms of each element using coefficients. This is exactly what we've done when we've balanced every other reaction that we've ever done. So we can see there's 2 bromine on the left here and only 1 on the right. So we would add a coefficient of 2 on that to balance our bromine atoms. We'd look at our iron on the other side. We've got 1 iron and 1 iron. That is already balanced. So that takes care of the first step. Next, we're going to determine the total charge on each side of the reaction. We're going to look at our ions with charges to help determine this, and make sure you take into account any coefficients. So once we look at the charge, though, we're going to balance the charge by adding electrons. Okay? So if we look at this, we've got no charge on the left, and we've got a 2 minus charge on the right. So that's 2 negative. So we're going to balance it with electrons. We're going to always add the electrons to the side with a greater charge to reduce the charge and make it the same. So our greater charge is 0. So we're going to add electrons to the left. And we need to add 2 of them. So we have a 2 minus charge on the left and a 2 minus charge on the right. For our other reaction, we can see we got 2 plus and 3 plus. So we want to add it to the side with the higher charge. So we're going to add it to the right side, and we only need 1 electron. That gives us a total of 2 plus on the right and 2 plus on the left. So these 2 steps are now done. All right, now we are going to continue balancing the reaction. So now that each half reaction is balanced by itself, we need to balance them with each other. We do this by making their number of electrons the same because they're part of the same reaction. The number of electrons gained or lost needs to be the same for both half reactions. So to do this, we look at the number of electrons added to each half reaction and find a common multiple based on their number of electrons. So for example, up here, we've got 1 electron and 2, so a common multiple would be 2. So we would want to make both reactions have 2 electrons. So to do that, we are going to multiply the reaction by a coefficient to make sure it has the correct number of electrons. We can, sometimes you'll only need to multiply one reaction by a coefficient, sometimes you'll have to multiply both by a coefficient to make them get the same number of electrons. And then we can just rewrite it with the proper coefficient. So it multiplies through, distributes just like you would in math. Now, the last part is to put our reaction back together. So we've got our half reaction for iron, our oxidation, and our reduction half reaction for bromine. They have the same number of electrons, and to put them together, we simply rewrite the reaction with the chemicals on the left that stay on the left, chemicals on the right will stay on the right side, and we eliminate the electrons because they are the same. Okay, so on the left we've got Br2. We can go ahead and put in their states of matter back now that we've got them all figured out. And iron 2+, it's aqueous. And that forms 2Br- and 2Fe3+, aqueous. We could see if we had just balanced the reaction like we normally would have up here, we would have probably just put a 2 in front of the bromine and called it a day. But that doesn't balance the electrons, the charge of the reaction. So by looking at the charge, we see that iron ends up needing a coefficient of 2. So we're going to try a couple more examples on the back. Let's take a look at them. So first we want to identify their oxidation numbers and find out who's being reduced and who's being oxidized. Iodine has an oxidation number of 0 because it's elemental by itself, no charge. Same thing for manganese. On the other side, they both have a charge, so that charge is going to be their oxidation number. So for the reduction reaction, the one that goes down in charge would be iodine, because it goes from 0 to -1. So I'm going to pull those pieces out. I2 forms I-. And for my oxidation, manganese goes up in charge, so we're going to have Mn forming Mn4+. So next we're going to balance the atoms on each element, or on each reaction. So I've got 2 iodine here, I would need 2 on the right side, and manganese I've got 1 on each side. Next we balance the charge. So I've got a charge of 0 on this side, but now a charge of 2- on the right side. So I'm adding 2 electrons, so they need to go to the side with the greater charge. So now I've got 2- on the left and 2- on the right. In our oxidation, we've got 0 on the left and 4+ on the right. We're adding electrons, so that brings down the charge, so we add it to the side with more charge. And we need to add 4 electrons to get the right side equal to 0. Now, we are going to balance the electrons. So we can see we've got 4 in this oxidation reaction, we've only got 2 in the reduction. So we're going to have to multiply our reduction reaction by 2. So it gives us 4 electrons plus 2 iodine compounds or molecules, forming 4 I- ions. Now that we have the same number of electrons in each, we can put the 2 half reactions back together. So on the left, we're going to have 2 I2s, and that's a solid, plus Mn, and that's a solid. On the right side, we're going to have 4 I-, aqueous, plus Mn4+, aqueous. So we can see we didn't really have to change much in terms of the coefficients on manganese, but we did on iodine. I will also point out that the order that we write these, just because manganese is first and then iodine, we don't have to make it match. It's the same reaction, no matter the order, as long as they're on the correct side of the arrow. Alright, let's try one more. Maybe pause the video and try this one on your own and then come back and check it. Alright, so hopefully you've checked it. So we should have a oxidation number +2, 0, +4, and +3. Alright, so our reduction, the thing that is going down in charge. Oh, we found this in class. Sorry, this is a typo. We ended up switching our 4+ and our 2+. Because there was a typo there. So we're going to flip those. Alright, so our reduction would have to be the tin. It's going from SN4+ to SN2+. And oxidation is the aluminum, going from aluminum solid to aluminum ion with 3+ charge. So now we're going to add in our electrons. On this we've got 4+ and 2+, so we want to bring down the larger charge. We need 2 electrons. That would make this side a 2+ charge and the right side a 2+ charge. In our oxidation, we need to add 3 electrons to this side to get that down to a charge of 0. Now you'll start to notice that your reduction always has the electrons added on the left because reduction is gain of electrons. Oxidation always has them on the right because that chemical is losing those electrons, they are breaking away. Now we've got to make the electrons the same on each. We've got 2 and 3. So a common multiple of that would be 6. So I want to multiply this one by 3 and our oxidation by 2 to get a common multiple of 6 electrons. So I'm going to multiply that 3 through the whole reaction and multiply this 2 through the whole reaction. And now we have the same number of electrons. So we can put our 2 reactions together for a balanced equation. 3SN2+, oh my gosh, I wrote 3+ instead of 4+. Plus 2 aluminum forms 3SN2+ plus 2 aluminum ion. You can always go back and put your states of matter: aqueous, solid, aqueous, and aqueous. Alright? So that's how we balance half reactions for oxidation reduction, and how we balance those reactions. We can also always check to see if if you're asked if a chemical reaction is a redox reaction, you can always use your oxidation numbers to help you see if they're changing and identify a reaction as oxidation reduction. Alright, thanks guys.